Hello, my name is Konstantinos Balaskas. I am a PhD student at the Aristotle University of Thessaloniki, currently at an internship with the Cultural Institute of Technology. Our work, Approximate Decision Trees for Machine Learning Classification on Tiny Printed Circuits, is a collaboration between the Aristotle University of Thessaloniki and the Cultural Institute of Technology. Here are some details on this speaker. Printed electronics is a fast-growing fabrication technology. It refers to the process of printing electronic devices on flexible or rigid substrates. Such devices range in the full spectrum of circuit design, making the production of fully printed systems a real possibility. Indicatively, there exist solutions for printed sensors, digital logic, antennas, display elements, and batteries and energy harvesters for storage functionality. The latter will in fact act as a criterion for power autonomy and efficiency later in this work. Printed electronics have seen a tremendous growth over the past years, becoming a key element in many industries. Several of its advantages as a technology paradigm open the door for numerous application domains and potential markets, which have not seen much infiltration from computational systems in the past. These domains may include the healthcare sector for sensing, monitoring, and informing professionals via wearable devices. Other candidates for printed electronics are industrial and environmental development or structural rigidness and health monitoring. Finally, considering that over $10 trillion fast-moving consumer goods market, disposables such as packaged foods, beverages, or consumables are sold largely without any embedded computing devices that could help with identification and tracking. For example, item tagging on consumer products must have a sub-cent cost requirement to meet the market specifications. Silicon technologies cannot provide such low-cost devices due to their high manufacturing and testing complexity. Printed electronics provides an alternative to silicon-based technologies since they offer different distinct characteristics. On one hand, conventional electronics are characterized by high performance and low area of their corresponding devices. However, they also include high per-unit fabrication costs, far higher than the cost of consumer products from the aforementioned application domains. Printed devices, on the other hand, have low fabrication and non-recurring engineering cost, making them suitable for applications with sub-cent product requirements. They can also offer flexibility, stretchability, and porosity benefits which are infeasible for silicon devices. However, they come with large feature sizes and elevated power consumption. Thus, printed electronics cannot compete with silicon technologies in terms of performance or area efficiency and transistor densities. Indicatively, their feature sizes are in the range of micrometers, compared to nanometers in silicon. Still, printed electronics offer an alternative mechanism for satisfying the requirements of different application domains. The advantages of printed electronics can be attributed to the manufacturing process of its elements. Manufacturing printed devices can generally be divided into two categories, subtractive or additive techniques. The step-by-step flow for both categories can be seen on the right. In the subtractive process, a series of additive or deposition and subtractive or etching steps are involved, similar to silicon-based processing. The subtractive method is relatively expensive compared to the additive, as it involves highly specialized processing, expensive equipment, and infrastructure. On the other hand, only deposition steps are involved in the additive manufacturing process. Transistors, passive components, and interconnects are realized by depositing material layer by layer. Generally, full additive printed electronics are slower compared to the subtractive-based printed technologies. Several contactless and maskless printing methods exist, with inkjet printing being the most prominent. It has attracted a lot of attention thanks to its highly optimized inks and printing capabilities on a wide range of carrier materials such as flexible substrates. Due to the simple manufacturing procedure, as well as low equipment costs, electronic circuits can be fabricated at drastically lower cost compared to silicon-based technologies. The research on printed electronics is limited in the literature and mostly involves circuits of low complexity due to the reduced area utilization they can offer. Such circuits include Boolean logic, storage elements, and amplifiers. Here, for example, we saw an inkjet printing low-voltage latch based on inorganic electrolyte-gated transistors. However, moving to more complex data flows has not been sufficiently explored. The cause of this are the prohibitively large feature sizes of printed electronic elements and their high parasitic capacitances, which lead to low functional densities and high device latencies. Machine learning classification algorithms are a great example of this. Their printed implementation is able to help several application domains by offering classification decision for consumer product details on the spot. Their power and area overhead, however, is prohibitively large. For that reason, conventional design techniques will be unable to implement such complex machine learning algorithms. Bespoke architectures are a great way to reduce the hardware overhead of printed circuits. Bespoke implies that there are hardwired coefficients in the architecture, for example, hardwired weights for a machine learning model. The low per unit and NRE cost of printed electronic elements allow for generating highly customizable architectures. Thus, bespoke machine learning classifiers can be implemented, tailored to their training data and application. These are classifier architectures that are customized to a model generated for a given application using specific training datasets, even at low to moderate volumes. Due to the simplified logic from the replacement of signals with constant coefficients, they offer decreased gate count designs and, as a consequence, significant area reduction. We demonstrate an example of this for an 8-bit unsigned comparator circuit, which is a basic building block for many machine learning classifiers. The conventional comparator receives two input signals and compares them, whereas in the bespoke implementation, one of the inputs is hardwired as a constant value. This modification leads to 5 times area reduction for this circuit. In this work, we study one of the most popular classification algorithms in machine learning, decision trees. A decision tree has a cascading structure of decision nodes to optimally allocate input data to classes by consecutively separating them. At the circuit level, nodes are represented by comparators. Bespoke decision trees decide upon the input features, that is the input data, and compare them to a given hardwired coefficient called the threshold. It has been previously shown in the literature that compared to other machine learning models, decision trees form perfect candidates for printed applications due to their lower area and power demands. We study fully parallel bespoke decision trees in this work, customized for a set of machine learning datasets as shown in the table on the right. We notice that most of the baseline circuits feature high area utilization, above 100 square millimeters, and significant power consumption. Specifically, some circuits cannot be powered by existing printed batteries, meaning their power is higher than 3 milliwatts. None of the baseline implementations can be self-powered by energy harvesters, meaning power lower than 0.1 milliwatts. We conclude that there is a need to further reduce the area and power of bespoke decision trees to enable their implementation and energy autonomy with printed electronic devices. As a starting point, we investigate the effect of different threshold values of comparators for bespoke decision trees of fixed precision. We conduct an exhaustive exploration for this purpose using all examined bit widths and possible integer thresholds. As shown on the right, we observe a high correlation between the area and the threshold value, here shown for two distinct bit widths of 6 and 8 bits. So, we discovered that some threshold values can be more hardware-friendly than others. We leverage this finding to approximate the decision tree structure at the comparator level. Specifically, we inject two different approximations into the baseline bespoke decision tree. First, we substitute the threshold of each comparator with a hardware-friendlier one in its vicinity. In detail, we define a range around the original threshold and include all values within it as possible substitutes. Secondly, we reduce the precision for both the input features and the hardwired threshold. We make sure that the new substituted threshold complies with the new precision of the comparator. It should be said that higher precision of the comparator circuit alone could possibly lead to larger area. However, at the same time, with our substitution technique, we get a finer granularity of possible substitutes, and thus the possibility of lower area. These trade-offs are later addressed by our heuristic optimization. Overall, we end up with an approximate version of the baseline decision tree, both in terms of precision and threshold value. By utilizing these two techniques, we are able to trade off exact computations, or alternatively classification accuracy, with reduced area and power. Considering that multiple options exist for each approximation technique, the design space of possible approximate decision trees is immense. Every design has a specific precision and approximate threshold value for each of its comparators. We therefore employ an evolution-based optimization to explore the design space efficiently. First, we translate the decision tree structure into a compact representation serving as the chromosome of the population. A chromosome, which represents a single approximate bespoke classifier, contains the bit width and the range to search for a threshold substitute for each comparator. The chromosome representations help in accelerating the standard iterative process of selection, crossover, and mutation, typically the core of evolutionary optimizations. Genetic algorithms are inherently parallel and scale very well to the available hardware resources. So, our Python implementation of the design space exploration can be conducted extremely fast. Also, we are not constrained by commercial licenses, which would be the alternative for accurately calculating the circuit's area. More on the area calculation later on. As the final product of the optimization procedure, we aim to obtain a set of close to Pareto optimal solutions in terms of both accuracy and area utilization. Here we present an overview of our automated framework. We start with a trained baseline bespoke decision tree using the training dataset. We dissect the tree structure to obtain its comparators. Then, we transform the threshold values into their integer and floating point representations. Floating point thresholds build the precision-scaled approximate decision tree to enable the precise calculation of its classification accuracy using the test set. Integers serve as the keys to a lookup table containing area measurements. Specifically, by knowing the integer form of a comparator threshold, we can calculate that comparator's area. We use the sum of comparator area calculations as a proxy for the area of the entire classifier. As explained before, a multi-objective genetic algorithm is employed to explore the possible trade-offs between area and accuracy. Each convergence is controlled by user-defined parameters such as the population size, number of evolutionary generations, and available threads for parallel execution. The evolutionary optimization converges to a Pareto front of approximate bespoke classifiers. We evaluate our framework on 10 different bespoke architectures for 10 classification datasets. The comparator area measurements with the substituted thresholds are obtained from the aforementioned lookup table. It is created from the exhaustive threshold exploration we performed using all examined precision bits for features and thresholds. We use a standard preprocessing step to prepare our dataset. We use a 70-30 split to create the training and test subsets, after which we normalize all values. We also utilize commercial EDA tools to evaluate our approximate classifiers after obtaining the Pareto front for each dataset. Specifically, we conduct synthesis to get the area using Synopsys Design Compiler, gate-level simulations with Mentor QuestaSim, extract the switching activity, which is used to calculate the circuit's power. We perform static time analysis with Synopsys PrimeTime for the circuit's delay information. The classification accuracy is obtained via sklearn by conducting inference with a test set. We present the final Pareto fronts from our evaluation procedure for all examined classification datasets. In green are the true area and accuracy measurements from our evaluation flow. Blue lines denote the estimated Pareto front from the optimization procedure, and the red star shows the corresponding baseline measurements. It can be observed that despite a few cases, the estimated Pareto front aligns very well with the actual measurements and provides a great proxy for exploring the design space of approximate bespoke decision trees. Overall, we observe that all of our approximate circuits for all datasets achieve lower area than the baseline. The majority of Pareto optimal solutions belong to a higher, non-dominated front than the exact classifier. That means that at least one of the objective metrics can be improved without deteriorating the other. In terms of accuracy, some classifiers achieve even higher accuracy than the baseline. This can be explained by the fine granularity at which we scale the precision of each comparator, which acts as a regularization measure to help produce a more efficient and less redundant architecture. On average, for the 2% accuracy loss threshold, our area reduction ranges from 1.7 to 5.7 times. For the more demanding 1% accuracy loss threshold, the area reduction remains almost the same, demonstrating the ability of our framework to find highly efficient bespoke classifiers with minimal accuracy loss. We evaluate our approximate classifiers with classification accuracy loss lower than 1%. We evaluate the hardware efficiency with respect to the baseline classifiers. Overall, we achieve an average area reduction of 3.2 times. Accordingly, our framework reduces the power consumption by 3.4 times on average compared to the conventional bespoke decision trees. To better demonstrate our area efficiency, we highlighted architectures with area lower than 100 squared millimeters and 20 squared millimeters. Such reductions allow for our approximate bespoke decision trees to be seamlessly implemented with printed devices, overcoming their area restrictions. Despite of the area-driven nature of our framework, our approximate circuits improve upon the power consumption of exact bespoke decision trees as well, allowing for more efficient implementations in printed electronics. Specifically, we highlight designs able to be powered by existing printed batteries, meaning their power consumption is lower than 3 milliwatts. We also obtained a design able to be self-powered with the use of energy harvesters, whose power consumption reaches below 0.1 milliwatts. In conclusion, printed electronics offer an alternative solution for lucrative application domains who haven't seen much infiltration of computation. This is attributed to the high per-unit manufacturing cost of silicon devices. We saw that machine learning circuits cannot be implemented with printed devices due to their large feature sizes in the fabrication technology. Bespoke classifiers offer a more hardware-friendly implementation, but are unable to overcome the power and area constraints of printed electronics in their conventional form. Using our framework, we generated approximate bespoke decision trees able to overcome such constraints. By inducing negligible or non-accuracy loss, our circuits achieve significant area efficiency and can be powered by existing printed batteries or even energy harvesters. Overall, our circuits enable classification to be seamlessly performed in tiny printed circuits. Thank you for your attention. Feel free to ask any questions directly or using the contact information.